intracrystalline diffusivity of gas molecules in zeolites and metal organic frameworks may significantly influence the separation performance for any given mixture separation task. The presentation today focuses on the determination of the diffusional time constant that quantifies the diffusional influences. The diffusional time constant is strictly defined as the Maxwell-Stefan diffusivity of the gas component I divided by the square of the crystallite radius of the zeolite or MOF. For background on the Maxwell-Stefan diffusion theory, I refer you to my YouTube presentation, Diffusion in Ordered Crystalline Microporous Materials. Today, I want to discuss how this diffusional time constant may be determined from experimental data on the transient uptake of unary guests. For theoretical background, I refer you to my papers listed here. We start our discussions of absorption-desorption asymmetry by considering the experimental data of Garg and Ruthven for transient adsorption and desorption, denoted by the red circles and green squares respectively, for uptake of ethane in LTA4A zeolite. 4A zeolite consists of a structure made up of cages, approximately 11 angstrom in diameter, separated by windows of dimensions are approximately 4 angstrom. Note that the sodium cations, of which there are 96 per unit cell, the sodium cations partially obstruct the window regions, and they influence the intercage hopping of gas molecules. Let's examine and analyze the adsorption and desorption kinetics by first resorting to the Fickian diffusion model to describe intracrystalline diffusion. Let's adopt the Fickian model to describe intracrystalline diffusion of ethane in LTA4A zeolite. In the Fickian model, we assert that the intraparticle flux, denoted by N sub I, is proportional to the gradient of the molar loadings, Qi. And this is the partial differential equation that relates the transient uptake to the intracrystalline diffusion fluxes. If we assume that the Fickian diffusivity is independent of the loadings, the partial differential equation describing uptakes can be solved analytically, and the expression for the spatially averaged component loadings can be expressed in this form. This is the Geddes model used for a variety of applications, such as in distillation, absorption, extraction, also for transient uptake in spherical crystalline materials. Using the experimental data, we can back out the diffusivities, the Fickian diffusivities for the transient adsorption and transient desorption. If we do that, we can determine that for describing the transient adsorption kinetics, the Fickian diffusivity divided by the square of the crystallite radius is 1.1 times 10⁻³ per second. However, for the desorption cycle, the experimental data is described by the value of the Fick diffusivity divided by RC squared equal to 6 times 10 to the minus 4. Put another way, there is an asymmetry in the adsorption and desorption kinetics. The adsorption kinetics appears to be faster by about a factor 2 as compared to the desorption kinetics. So let us examine the reasons why the asymmetry occurs. And to do this, we have to adopt a more fundamental approach to intracrystalline diffusion by properly recognizing that the driving force for intracrystalline diffusion is not the gradient of the molar loading, but rather the gradient in the chemical potential. If we adopt the Maxwell-Stefan diffusion formulation, the intracrystalline flux Ni is written in terms of the gradient of the chemical potential in this manner, where Qi is the molar loading of component I, R is the gas constant, T is the temperature, and we have the chemical potential gradient of species I. If we compare this expression with the Fickian expression shown on the previous slide, we can derive a relation between the Fickian diffusivity D with the Maxwell-Stefan diffusivity D with a line through it, and the relation shows that the Fickian diffusivity equals the Maxwell-Stefan diffusivity times a thermodynamic factor. The thermodynamic factor is determinable from the adsorption equilibrium that relates the molar loadings Qi to the partial fugacity in the bulk gas mixture F sub I. If the adsorption equilibrium is described by the single site Langmuir model, Qi divided by Qi at saturation, which is the partial occupancy, is the Langmuir constant times the partial fugacity in the bulk gas mixture. And we can determine the thermodynamic correction factor to be 1 divided by 1 minus theta, but theta is the fractional occupancy. And if we examine how the thermodynamic correction factor depends on the fractional occupancy, we note that at zero occupancy or very low occupancy, the thermodynamic correction factor is unity. But as the occupancy increases and approaches unity, the thermodynamic correction factor increases exponentially in this manner. During the adsorption cycle, we proceed along this way, and in the desorption cycle, the thermodynamic correction factor decreases because the occupancy is progressively reduced. Now, if we examine the Fick diffusivity and equals to the Maxwell-Stefan diffusivity times gamma, we note that in the adsorption cycle, the Fick diffusivity would increase with fractional occupancy, whereas in the desorption cycle, the Fick diffusivity would be a decreasing function of the fractional occupancy. And the adsorption and desorption cycles can both be modeled reasonably accurately with the value of the Maxwell-Stefan diffusivity divided by the square of the crystalline radius equals 2 times 10 minus 4. And the reason that the adsorption kinetics is faster is due to the influences of the thermodynamic corrections. And using the Fickian model, we have to account for the faster adsorption kinetics with a Fick diffusivity divided by RC squared value of 1.1 times 10 minus 3, and the desorption cycle is described by the Fick diffusivity divided by RC squared value of 6 times 10 minus 4. The asymmetry is engendered by the behavior of the thermodynamic correction factor. Taking due account of thermodynamic corrections, both adsorption and desorption cycles can be described by a unique value of the Maxwell-Stefan diffusivity divided by RC squared equals 2 times 10 minus 4. And this underscores the importance of using a more fundamental description of intracrystalline diffusion. Further background information is provided in this publication. See also my videos on diffusion in ordered crystalline microporous materials on my YouTube channel.